Hi everyone, I'm Fazil Imtiaz and I'm the team lead of Team Neural Ninjas. Our problem statement ID is 25231 and our theme is smart automation and our problem statement category is software. So let's start with our multimodal agentic retrieval system explanation. I'll explain it to you through a workflow diagram. So our first step in this is data ingestion. Data ingestion starts can be done automatically at a scheduled interval or manually by a system admin. The goal here is to start collecting enterprise data from documents, research papers, internal reports, meeting audios, or even infographics into a single unified input source. Our second step is user placing files in data raw folder. This folder acts as a staging area for all types of input data such as PDF, docs, images, or WAV audio recordings. Each file added here automatically triggers the injection workflow through a file watcher or orchestrator like LangGraph, ensuring the process is smooth and reactive. Our third step would be type decision node. In it, our decision node checks the file extension and routes it to the appropriate processing module. This module design ensures scalability, and for example, if we want to introduce a new file type like CSV file in the future, it would require minimal code changes. It also reduces our training costs. Our fourth step is text file processing. For text-based documents such as PDF or docs, we use libraries like PyMu PDF to extract clean text from the raw document. Once extracted, the next step is text chunking. Here, large text blocks are divided into smaller, semantically meaningful chunks, usually around 500 to 1000 tokens each. Chunking helps in maintaining context coherence and ensures embedding don't lose semantic meaning. Our fifth step is image file processing. For image data, we skip textual extraction and move directly to image embeddings. Here, a vision encoder model such as OpenAI's Vision API converts images into vector representations. Each vector captures high-level semantic features like objects, patterns, or even relationships between the visual elements. These embeddings allow the system to answer image-related queries. Our sixth step is audio file processing. For audio data, we perform audio transcription using a speech to text model which we have used as OpenAI Whisper. This converts spoken language into text with high accuracy. The resulting transcription then undergoes audio chunking similar to text chunking to segment the audio transcript into smaller meaningful parts. This helps when performing semantic search across long recordings like interviews or podcasts. Embedding creation. After processing all the different types of data, we text, image, and audio transcripts are transformed into vector embeddings. Embeddings are numerical representation in high dimensional space that captures semantic meaning. For instance, two images or sentences with similar meanings will have embeddings close to each other in a vector space. We use embedding models like OpenAI embeddings for this task. Indexing in vector space, vector store. These embeddings are then stored as vector databases such as LansDB. Vector stores are optimized for fast similarity searches, enabling us to retrieve semantically related content within a millisecond. Each record in a store contains not just the embedding but also the metadata like source file, chunk ID, and time stamp, which is crucial for explaining. Our ninth step is ingestion complete. With this step, the whole ingestion part is complete. The system holds the multimodal knowledge base ready for intelligent querying. Our second phase is querying handling. In this phase, our first step would be query start. This the user initiate a simple query through a simple and intuitive radio interface. They can ask natural language questions about the topics, and our second step would be orchestration. The next stage is orchestration, which means which we are using LangGraph. LangGraph is a powerful framework for chaining and controlling multi-agent workflows. It coordinates the movement of the user's query through the retrieval, reasoning, and response stage. This modular orchestration ensures the system is transparent and debuggable. Third step is retrieval agent. LangGraph, which is also called retrieval agent, which is responsible for fetching the most relevant information from the vector store. It uses the query embedding, a vector representation of the user's questions to perform a similarity search. The top k results, often the closest vectors, are retrieved as candidate context chunks. Our fourth step would be semantic search in vector store. The retrieval process relies on semantic search, meaning it understands the meaning, not just the keywords. So even if you have not asked a particular keyword in a query, it will in the answer part it will give that words, and you can find the relevant passages in the answer. So our step 5 would be context compilation. The retrieved chunks are merged to create a context document, a concise yet comprehensive representation of all relevant information. This ensures that the next stage, the language model, works with grounded and accurate data. Our sixth step would be LLM agent and grounded answer generation. This context is passed to the LLM agent, which could be powered by any open source model like Qwen and Llama. The LLM doesn't hallucinate here, as it's grounded in retrieval facts using the RAG approach. The model synthesizes the retrieved content to produce precise and explainable response. Our last step would be the generated answer. Like the system can optionally provide citation or reference links in the answer, ensuring full transparency. Once done, the query is marked as complete. We have also added the feature of multi answer generation. In conclusion, our multi-model agentic RAG system brings together the best of multiple AI disciplines, which are natural language processing, computer vision, and speech recognition, with agentic AI in a single orchestrated pipeline. It can ingest diverse data formats to build a unified knowledgeable base and deliver semantically rich grounded answers, making it ideal for enterprise knowledge system, academic research, or AI powered assistant. Now I show you our live demo.